The genesis of life. The origins of life represent one of the most profound and enduring mysteries of the universe. It's a scientific enigma that connects the disciplines of physics, chemistry, and biology, while simultaneously captivating the minds of anyone curious about where we, and possibly other life forms, come from. Science enthusiasts, brace yourselves. Today, we dive into this fascinating topic to explore the conditions that allowed life to emerge on Earth and what this could mean for finding life beyond our planet. The story of life began approximately 3.8 billion years ago, when early Earth was a chaotic, unforgiving world. Volcanic eruptions, lightning storms, and a chemically rich atmosphere gave rise to what scientists often call a primordial soup. This broth of organic molecules served as the raw material of life, energized by forces like sunlight, geothermal heat, and chemical reactions. But what were the essential conditions needed for life to appear? The recipe for life isn't as simple as throwing random elements together. Science has identified three crucial factors: an energy source, the availability of water, and the presence of organic compounds. From the simplest amino acids to nucleotides, these building blocks of life likely arose through chemical interactions, both on Earth and in the vast expanses of space, hitching rides on meteorites and comets that collided with our planet. One groundbreaking experiment, the Miller-Urey experiment of 1953, recreated this primordial environment in a laboratory setting. Researchers passed electrical sparks, mimicking lightning, through a mixture of gases thought to resemble early Earth's atmosphere. The result? The spontaneous formation of simple organic molecules like amino acids, the precursors to proteins. This experiment proved for the first time that life's ingredients could arise naturally under the right conditions, setting the stage for further exploration. As science enthusiasts, it's crucial to ponder: could similar processes have occurred elsewhere, on other planets or moons? If Earth's chaotic beginnings nurtured life, what does that say about the potential for life under similarly harsh conditions in distant cosmic neighborhoods? While the spontaneous formation of organic molecules was a vital first step, life's next challenge was to organize itself into something more. Enter the miracle of self-replicating molecules, the chemical ancestors of DNA and RNA. These molecular pioneers were capable of making imperfect copies of themselves, giving rise to a process we now recognize as evolution via natural selection. Over millions of years, these self-replicating molecules gradually transformed into organisms capable of metabolism, reproduction, and adaptation. Early life flourished in Earth's oceans, where the depth provided a natural shield from harmful ultraviolet radiation. Hydrothermal vents on the ocean floor likely played a critical role, spewing out nutrient-rich fluids and energy that gave primitive life forms a stable environment to thrive. For science enthusiasts, this phase of evolution sparks important questions for discussion. What were these self-replicating molecules really like? Could life's leap from chemistry to biology have followed the same path elsewhere in our solar system, say, beneath the icy crusts of moons like Europa or Enceladus? One of the most exciting developments in recent decades has been the study of extremophiles, organisms capable of surviving in conditions once thought utterly inhospitable. From searing hydrothermal vents to sub-zero glaciers, acidic hot springs, to environments with crushing pressure, extremophiles reveal the adaptability and resilience of life. These discoveries expand our understanding of life's parameters, showing that biology can persist in environments previously deemed lifeless. Take, for instance, microbes thriving in the boiling hot springs of Yellowstone National Park or tiny tardigrades enduring the vacuum of space. Such findings inspire bold questions. If life can survive extreme environments here on Earth, could similar organisms exist on extraterrestrial worlds? Perhaps in Mars's underground reservoirs or the methane lakes of Titan, Saturn's largest moon. Understanding extremophiles isn't just academic curiosity. It's a game-changer for astrobiology, the discipline dedicated to searching for life beyond Earth. The resilience of life in extreme conditions opens the door to imagining life forms that defy our traditional expectations. Let's venture outward from Earth. Within our solar system, two locations have captured the imaginations of astrobiologists: Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Both boast subsurface oceans hidden beneath ice crusts, but likely heated by tidal forces. These pockets of water, combined with organic materials and energy, are prime candidates for hosting life, albeit microscopic at best. Even further afield, discoveries of exoplanets in distant solar systems keep fueling hope. Many of these planets orbit within the habitable zone, the Goldilocks region, around a star where conditions might support liquid water. The search for biosignatures, traces of biological activity, like oxygen or methane in a planet's atmosphere, remains one of the most exciting scientific pursuits of our time. Science enthusiasts may already be asking, what would discovering extraterrestrial life mean for humanity? How would it redefine our understanding of biology, chemistry, and our place in the cosmos? As telescopes like the James Webb Space Telescope revolutionize our ability to study distant worlds, these questions edge closer to answers worth sharing and debating. Ultimately, the search for life, whether examining Earth's primordial past, today's extremophiles, or the rocky surfaces of distant moons, reminds us how extraordinary biology is. Life's ability to adapt, evolve, and survive against staggering odds speaks to the remarkable interplay of physical laws and chemical possibilities that make existence possible. So, fellow science enthusiasts, the next time you gaze at the stars or ponder our origins, remember, life is not just a biological phenomenon, it's a cosmic story. And whether or not we discover evidence of life elsewhere, the journey to uncover our place among the stars is a legacy worth discussing, celebrating, and exploring. Thank you for joining this science conversation today. If you've enjoyed diving into the mystery and science behind life's genesis, help spread the word. Comment with your thoughts, share this video with like-minded friends, and let's continue the discussion about life, the universe, and everything in between.